Alright, super fun project today. I published a video recently on this DIY 12-volt lithium iron phosphate battery using EVE cells and a JK-BMS, and then I compared it to the cost of some other options that I had experience with. In an attempt to keep the cost down, it's a completely bare bones assembly with no case. So you'd have to put it on a shelf or something. It's not very portable. But most people will want a case. It gives it some protection and it allows you to carry it around a lot easier. So today I have a much simpler build using this DIY battery kit from EVE. Welcome back to Project with Everyday Dave. It's time to build this DIY lithium iron phosphate 280 amp hour battery, and then we'll run some tests and see what it can do. You can source your own batteries and order just the case from EVE. But for this build I ordered everything from EVE so you can understand what they offer. First, let's take a look at these cells. These are high quality 280 amp hour lithium iron phosphate EVE cells. They were delivered in great shape, perfectly flat, nice and clean, no damage, really well packaged. They also come with flexible bus bars, which is really nice. I don't know anyone else who does that. I'll put the serial number of one of these up on the screen here just for reference. If you've done any investigation on DIY battery builds, you've probably run across Andy's Off-Grid Garage channel. His channel is a great resource for all kinds of charging and discharge settings for your DIY batteries, so be sure and check out his channel. Andy's also a fan of this battery tester, so I ordered one to try out for all of this battery testing I'm doing for this project and a whole bunch of other ones I have lined up in the future. I ran a capacity test on these 280 amp hour cells that we're using and they performed very well. You can see from this chart I charged the battery to 3.65 volts. Let it sit for 30 minutes, then discharged it at 35 amps down to 2.5 volts. And that resulted in a capacity of 284.6 amp hours, just over the 280 amp hour rating. After the capacity test, I charged it back up to 3.3 volts to make them all the same for our assembly. Now that I'm happy with my cells, their charge level and performance, let's take a look at the kit. Now I have to say, I really like this battery box. It's really attractive, has nice features, has little indents here for picking it up, and it's just really well made. It might be a bit more expensive than buying a toolbox at the hardware store, but it comes with a lot of features built in and everything you need for assembly, so I don't think it'll be hard to justify the cost. The BMS distribution board is temporarily set to the top, and then we have all of our equipment here on the inside. It's interesting how they've gone through the trouble to heat shrink some of these, but not all of them. A little bit of sealer on that ring. Be sure and get that off of there, otherwise we'll have a bad contact. Alright, now we can get to all the pieces on the inside here that was shipped with it. Neoprene spacing material, phenolic insulating panels, another piece for the top, nice flexible bus bars for connecting the main terminals. Look at that. All the nuts and bolts in a nice little carrying case. I really like that. It's like attention to detail, you know? We have our fuse, all the fasteners. That's pretty slick. The terminals that'll stick out of the end of the box. And I guess this is the BMS. Well, it comes with more heavy-duty bus bars. Ooh, that's really nice. These bus bars have an additional mount for the sensing wires. That way we don't have to degrade the connection with the battery by having that sensing terminal under that main lug. That is a really nice detail. Power switch, terminal covers, wiring. Whoop. And there's our BMS with 2 temperature sensors. And that's really nice. JK-BMS, that's something most of us will be familiar with. All right, we have all of our pieces. The quality looks great. The case is just really well built and sturdy. I'm having a hard time hiding my glee here. I really like this case. I'm hoping that it performs as well as it looks. All right, this battery box is built just like the large 48 volt DIY packs. It has structural reinforcements through the entire thing. The front cover can be removed. It has a compression plate to compress the batteries and hold them in there nice and tight. This is just a really fantastic build for a 12 volt battery. So let's pop that plate off and see how our batteries stack in there. Just have a little magnet on the side of the case here so I don't lose my screws. Wow. Man, that is nice. First step will be to apply our phenolic insulators on the top, bottom, and sides. Now I can slide the batteries in. There are 2 pieces of EVA foam that will help space them out and give us a little bit of resistance against the compression plate. These batteries have to be installed in the correct orientation, so I'll show exactly what that is here on the screen for reference. We'll just stack these in here. You're supposed to space these evenly with the EVA foam, but I'm going to put both pieces of foam in the middle so that I can fit one of these temperature sensors in there. So I'll start with an insulator, positive on the side, then a battery, then an insulator, 2 pieces of foam, then another battery. Now let me see if I can fit my temperature sensor down there. Measure about halfway down. All right, that's working pretty well. I pushed the EVA to the left so that I could slide my temperature sensor about halfway down the battery. And even with compression, I can still move it up and down a little bit, so I know it's not going to get crushed by the batteries when I bolt the plate on. So that gives me some temperature sensing down within the pack, and then the other sensor I can place somewhere on the top once we get the rest put in. That's what I'm going to do with that. Then we'll have one more insulator, the last battery, final insulator, and a plate. And that gives us just a tiny little bit of compression against the cells. Man, that is absolutely perfect. All right, now we can bolt this on. And I don't have to worry about the torque. The EV foam will give us just a little bit of compression. I can tighten them all the way against the back, and that'll give us pretty much the right amount of compression. Nice, that worked absolutely perfectly. Let's get the rest of this put together. All right, the instructions say to put the insulators on the bus bars before you install them. And I really like this idea. One of the things I've noticed about this build is the batteries come with protections on the terminals, the bus bars have protections on them. They really go out of their way to limit accidental contact. Now, with our batteries in position, set the torque wrench to 5 Newton meters. And you do want to use a torque wrench for these. They need to be set to the right amount. If you don't get them tight enough, you're going to have heat issues. And if you get them too tight, you can strip the studs, and neither one of those is a good scenario. Now, to get our 13.5, 14 volts, we're going to put these 3.3 volt batteries in series. So this will be the negative, and we'll go to the positive of this one, connect that to the negative of this, and we'll make our way around till we get to our 13 plus volts. In order to do that, we'll have to connect these two, and these two, and these two. Because these covers go underneath the bars, you'll want to make sure that you do not get any of this rubber under the contact surface for the lugs. So I'm going to push that back fairly far, make sure that I don't have any risk of contact there. All right, now my torque wrench is set to 5 Newton meters, and I can go ahead and torque these down. Now before I cover these up, we're going to set the PCB board on here. And this also comes with a piece of EVA, and those clearance holes are for the blow-off caps. So I can go ahead and peel this and stick it to the back side. All right, now I can secure the PCB board. And there's a couple extra screws in the PCB board itself. All right, now I want to connect the sensing wires. And we need one on each one of these bus bars. That's what the BMS will use to understand the voltage of each one of the cells so it can maintain the cell balance. And the really nice thing about these bus bars is it has separate mounts for these wires so they don't have to go under the main terminals. That is fantastic. What isn't fantastic is trying to fish them under these covers. Okay, I really like the boots, and it saved me from having to put some tape over that because I don't like to accidentally touch things, but I could understand if you left them off because it's a real pain in the butt to get these sensor wires under there and screwed onto their terminals, since the fastening point, is very far underneath. But I got them on there. It's doable. Now, before I get the BMS and everything connected, I want to check the voltage across the terminals and make sure that we have everything connected right, because you don't want to do it backwards. So I should have a little over 13 volts across the final terminals and 13.16, so everything is connected properly. Now these last two sensing wires are going to be installed with these terminals. So the next step is actually to mount the BMS, and it mounts right to the PCB board bracket. And the BMS always connects to the negative terminal on the battery. So the B minus terminals will go to the negative terminal of the battery. We don't actually directly connect to the negative terminal on our outside post. And then the P minus power delivery end of the BMS will go to the negative terminal on our exterior battery case. They've included this very nice flexible insulated bar for our negative terminal. I don't know, it's a little bit tight. I think, it's not bent in exactly the right place, so it's just a little bit offset from where it should be. How do I solve that problem? I really like these flexible bars, but this one wasn't bent in exactly the right place, and I've twisted it around a little bit in order to get it to fit without putting undue stress on the components. And I think I've got it there. And then this black wire connects to that terminal to get our negative end. Make sure that you don't get any shrink tube under the nut. Now I just snug these up to make sure that everything is right where I want it before I tighten things down. Then I can torque these down. Sweet. Next I need to mount the on-off switch and the battery terminals to our front plate. That's the nice thing about using this JK-BMS. It has an on-off switch. It allows you to turn power on and off to the battery physically. Positive terminal will be on the left side of the battery here, and I want to make sure that the bar is facing up for the connection to the terminal. Be sure to temp set them all before you tighten them up, or you might not be able to get the screws to align. All right, front face is ready to put on the battery. One of the temperature sensors we slid down in between the cells, and this other one I'm just going to set up on the top of the cell and wedge it under this insulator, and that holds it pretty well right against the cell. Then we'll go ahead and plug that in to make sure it's out of the way while we're putting the final bus bar on. Then the on-off power switch goes to the middle connector, and then there's another cable that connects the PCB board to all of the voltage sensors. Now we just need to connect the negative bus bar, and that's this guy. And just like the other one, it is just a little bit, it's just a little bit tight here on this end. So you can see the holes just don't quite line up, and I can push it pretty far or pretty hard over and it still won't line up. So I think I'm actually going to have to egg those holes out a little bit. All right, I actually didn't have to egg them out. I just put this on the edge of my vise and gave it a little tap with the hammer, and it squared this corner up. And now I can get those screws in there. Now in this case, I'm actually going to tighten these first so that I can flex the cable around. We'll just set this to 5 Newton meters. Now I can tighten that final bolt, and that flexes in place, no problem. All right, now this final connection is actually made with this 250 amp fuse. So we'll drop that on there. So our final voltage sensor goes in with that. Make sure that the nut doesn't pinch any of that insulation. And it is going to touch it, so trim just a little bit of that. Temp set that side. There are boots that we could have used for the last terminals, but I think they just get in the way, so I left those off. Now I'm actually going to turn it on and set the BMS and make sure everything works properly before I put the lid on. All right, moment of truth. Let's see if it powers up. That's it. The BMS started up, power light's on. Let's connect to it with the app and get it set up. All right, with the BMS on, I should be able to find it in the app. Download the JK-BMS app and start it up. Try this one. That was it. The beep, beep, beep tells me it's connected, and here it is with all the stats, 13.16 volts. All right, there's a few settings we're going to want to change, and to be able to change all of the settings, I need to put in a password. So I'll click on Verify Password. The password's 1, 2, 3, 4, 5, 6. Verify. Okay, and then the first setting that I want to update, I'll click on lithium iron phosphate, LiFePO4. And that'll switch the basic settings over to that, and you don't want to hit that again after this because it wipes everything and sets it back up. Then we'll change the cell count for OK 280. Okay. 005. Okay. And in the advanced settings here, you can adjust all kinds of things, and you can look at some of my previous videos on the DIY battery, or look at Andy's channel, Off Grid Garage, if you want to get into all of these details. But the base settings should work fine out of the box. So we're going to go with those for now. Looks like everything is set up and working properly. I'll go ahead and put the lid back on, then I can charge it up and do a capacity test on the entire battery. And I'll connect it to an inverter and we'll run a few things and make sure everything works great. And then we'll compare the price to the DIY version. Forgot there's one more thing we need to turn on here under controls. 1, 2, 3, 4, 5, 6. And we want to be able to charge and discharge. All right. There we go. All right, now it's giving out power. I can see it on my shunt. So I can go ahead and connect my charger up. We'll charge it up. All right, I hooked up my 40 amp charger and I went to charge and it started charging and then stopped. I'm like, what? Why in the world isn't that working? And then I went to the advanced settings and I see that it's set to 25 amps as a maximum, which is ridiculous. This BMS can handle 200. So I'll put this in 150. All right, now we should be able to charge. I can turn my charger off and back on again. Now I can see it's charging at 40 amps, 38.7, 39.5. Those are pretty close. 523 watts going into the battery. Everything's happy now. Charge is on, discharge is on, balance is on. You can see the balance current there at 2 amps. And you know, one of those cells I completely discharged and then recharged to the same voltage, but the voltage curve is so flat on lithium iron phosphate batteries, it doesn't mean that I got it charged to the same capacity. We'll probably use that 2 amp balancing current quite a bit to get these balanced out. I'll give it a chance to make sure it's completely balanced before we do our discharge test. All right, we're working now. Get her charged up. All right, I'm using my Renogy 2000 watt inverter, pulling 1500 watts and 130 amps out of the battery continuously for almost 2 hours now, so we can do our capacity test. So let's use the thermal camera and see what it looks like inside. Okay, so the hot spots on the inverter there are 38 degrees Celsius. We have some warm spots, 50 some degrees on the wiring. BMS has some warm spots there. Still no more than 50 some degrees Celsius. That's pretty good. And you'd expect the fuse to be a little bit warm, but none of our connections are unusually warm, so that's good. I put my hand in there, you can kind of see the temperature difference. My hand is 32 C, and you know, it's warm to the touch, but not too bad. The outside of the case is cooler than my hand. All in all, pretty good. For most people, you won't have to worry about any issues with temperature, but if you live in a hot climate and you plan to run close to that 200 max for long periods of time, you could cut a slit in the top of this lid and mount a fan to the front and actually pull air across the BMS to improve the cooling performance. But you wouldn't want to do that unless you lived in a place with low dust and low moisture. You don't want to be pulling moisture or dirt across those components. I think for most people, you just keep it just like it is. Well, I ended up running the capacity test twice. The first time I got 280 amp hours on the Victron shunt, and I know it has more capacity than that based on the individual cycle test. I noticed that the one cell I used for my cycle test was a little undercharged compared to the rest, slightly limiting the full charge and discharge points. Over a few cycles, I'm sure the active balancer would fix that, but I didn't want to wait. And the nice thing about a DIY battery is you can check the individual cells and fix them individually if you want to. So I just opened the lid and used my charger to charge that individual cell directly. A really cool result was, as that cell finally came up to voltage, the active balancer started shifting power from that cell to the other ones to keep them all at the same level, even though I was charging just that cell by itself. That was pretty neat. With every cell balanced, I ran the test again, and this time I got the full capacity I was seeing on the individual cell level for the whole pack, 285 amp hours, which is 5 amp hours above the 280 amp hour rating for these cells. And that is a great result. For some perspective on performance, let's power some typical off-grid activities. I've connected the battery to the most popular inverter on Amazon, the 2000 watt Renogy. We'll brew some coffee with the Keurig, air up some tires with the pancake compressor, then clean up with full-size shop vac. I've included the Victron shunt and the battery BMS on the screen for reference. So let's brew some coffee. All right, we're pulling about 120 amps. Almost the same as the hot water heater element. So this thing draws a tremendous amount of power. You're thinking, oh, I'm just brewing a little bit of coffee, but it is a huge power consumer. You can see cell number 4 is now the one that is the lowest voltage, so it has finally evened out all the cells. I don't have one that's performing better than another. I really like that 2 amp active balancer. It really helps make sure all the cells are always in balance. Well, you can see that it stopped heating the water because the power dropped off. And there it goes. There we go. With the coffee brewed, it's time to get to work. All right, let's check the pancake compressor. It's a big startup surge, but the running load isn't that high at just under 90 amps. And now time to clean up with the shop vac. A little higher at over 100 amps, but no problem. Now you can see that this setup can power most devices in the average home, but it will not be able to do large shop tools like a full-size dust collector or a full-size air compressor. I recently did a video comparing 7 12-volt inverters so that you can pick the one that will meet your needs and your budget. I'll link to that video in the description for your reference. Let's take a quick look at the cost. My bare bones DIY battery was $493, and it used similar 280 amp hour EVE cells. The batteries I sourced for this DIY battery were slightly higher capacity, but they're essentially the same. And they both use the same JK-BMS, so the performance is pretty much exactly the same. Now, for $730, you can get this battery pre-assembled from EEL. That is the most convenient method. You get a battery that has all the flexibility of a DIY battery without any of the work, but the fully assembled version is shipped from China, so it takes some time to get it. You can buy just the case, and it's $270, and it is stocked in the US. If you want to save a little money, you can order just the case from the US stock and source your own batteries like I showed in my DIY version. That would save you over $100 a battery, and you get the materials from US stock very quickly. Either way you do it, I think this is a great solution for a 12-volt battery. And it's really not a bad deal considering the quality and flexibility you end up with. On top of that, EEL is offering a special discount for my viewers using the discount code in the description below. If you're interested in building one of these batteries, I wouldn't wait around too long. With the tariff situation, prices are fluctuating around a lot and stock may vary. I also have discounts and sources for just the raw cells. If you want to see all the discounts and deals that I can offer, just go to the battery tab on my website, projectwithdave.com. On my website, you'll also find lots of resources like a free solar calculator and all kinds of resources on how to develop solar systems for your own DIY projects. If you want to watch the bare bones DIY build, watch this video right here. And if you want to see 7 2000 watt inverters tested back to back, watch this video right here. My vertical solar panel test with the addition of the north-south facing panels is shaping up to be very interesting. So be sure to subscribe so you don't miss out on those results coming up soon. Thanks for watching, and I'll see you next time.